Hi everyone! Let's review some wave properties today. So the reason why we're reviewing some wave properties is because the name of this unit is the wave nature of light. So obviously if we want to describe light as a wave and light interacting as a wave, we need some wave terminology and wave properties. Now, the first person to really put together the idea of light as a wave was this guy named Maxwell, James Clerk Maxwell, in 1864. What he did was he compiled all of the results of other scientists concerning electricity and magnetism. So people like Gauss and Faraday and Ampere, who took a lot of qualitative and some quantitative results concerning electricity and magnetism and the behavior of electric and magnetic fields. Now, Maxwell put them all together into four very important equations, which are called Maxwell's equations. And he was very surprised to discover that what he had actually described was a wave, a time-varying electric and magnetic field. He was describing light, and that was a shock to everyone. These are the four equations, Maxwell's equations. Now, you do not have to understand these equations, but they're very nice equations, so I'm going to show them to you anyway. The equation at the top is basically a summary of the fact that electric field lines point outward from charges, and they depend on the amount of charge enclosed. This second equation basically tells us that magnetic field lines are closed loops with no beginning or end. The third equation explains a result that we've heard before, that if we have a changing magnetic field, it will induce an electric field. This is how electricity is generated, for example. And our final equation also summarizes a result that we've used before. An electric current, or time-varying electric field, will produce a magnetic field. One conclusion that he drew from this data is that a changing electric and magnetic field can be self-sustaining, like a wave. It can travel through a vacuum. He also calculated the speed of this wave. The speed of the wave is given by a couple of constants that show up in our electricity and magnetism equations. And by manipulating those constants, he actually came up with the speed of light. Now, at the time, people had measured the speed of light, and they were also shocked to learn that's what he has just described in his equations. So this was some pretty conclusive evidence that light is a wave. In fact, an electromagnetic wave consists of in-phase, time-varying electric and magnetic fields that are perpendicular to each other. The direction of travel of this wave is perpendicular to both the electric and magnetic field, and we will visualize it as a transverse wave. In this animation, you can imagine the red transverse wave represents our electric field, the blue transverse wave represents our magnetic field. And let's imagine it's moving forward, it's propagating at the speed of light. Here's a quick refresher on some wave properties. First of all, the period of a wave is just the time taken to complete one full cycle or oscillation measured in units of seconds. The frequency of a wave, which is just the reciprocal of the period, is the number of cycles or oscillations that happen every single second. So the most common unit is hertz, which just means cycles per second. The wavelength of a wave is the distance between consecutive points on a wave measured in meters. And finally, the amplitude of the wave is the size of the greatest deviation from equilibrium of whatever it is that's being disturbed. In the past, when we've talked about mechanical waves, we talk about particle displacement, and so amplitude was measured in meters. Now we're talking about electric and magnetic fields, and so it's going to be a little bit of a different way of describing amplitude. Here are a couple of equations that are going to come in handy, as they always do when it comes to waves. The period and frequency are reciprocals of each other. And finally, we can relate wavelength, frequency, period, using the following equation. The speed of the wave is equal to lambda, the wavelength, times the frequency in hertz. There are a few different types of waves. However, when we talk about light, we're talking about a transverse wave. In transverse waves, the oscillation is a displacement perpendicular to the direction that the wave is traveling, or the wave's velocity. In the case of light, we're talking about a variation in magnitude of electric and magnetic field. For longitudinal waves, which we're not talking about this unit, Oscillation is a displacement that is parallel to the direction that the wave travels. A good example of a longitudinal wave is a sound wave. Finally, there is another type of wave called a torsional wave, where oscillation is an angular displacement, back and forth, about some axis that we define. And that axis is the direction of the wave velocity. For this transverse wave, the amplitude and wavelength are labeled. So you can see the wavelength is just the distance between 2 points that are in phase on a single wave. And you can measure wavelength on any 2 points that are in phase on a given wave. Doesn't matter where it is. Amplitude is always a magnitude, so it's always the maximum displacement of whatever it is that's oscillating. When we describe two waves that are out of phase, when they're not perfectly overlapped in space, we're actually describing a phase difference. We can describe that in terms of what fraction of a wavelength are they offset. We can also describe, instead of using wavelengths, an angle measurement in radians or degrees that they are offset. So here's an example. We have this red wave, but let's say the blue wave isn't actually in phase anymore. There's some sort of phase difference. If I wanted to offset the blue wave by 90 degrees or pi by 2, I could shift it this way, which is a 90-degree shift. I could also shift it this way, because I didn't really specify direction. That's another 90-degree shift. I can also describe that as a shift of a quarter of a wavelength. Those are equivalent ways of describing a phase shift. When two waves or pulses overlap, they occupy the same space, their amplitudes are going to add as vectors. When amplitudes add to result in a greater overall amplitude, that's called constructive interference. When the amplitudes subtract to result in a smaller overall amplitude, that's called destructive interference. In this example, you can see two simple waves traveling past each other, undergoing superposition. The new wave is represented in white, and you can see examples of both destructive and constructive interference. Here we have two waves that are emitted by a source, and when they're emitted at the source, they're emitted in phase. However, they travel different distances before they meet in space. As you can see, the wave at the bottom coming from source 2 has to travel farther. And so when these two waves overlap, the wave at the bottom is at a crest, while the wave at the top is at a trough, meaning at this particular point, they're going to undergo perfectly destructive interference. In the example below, the sources are shifted a little bit. They are still emitting the same wave in phase from the source, but now wave number 2 has to travel even further. So when the two waves overlap in space, they happen to both be at a crest, meaning you're going to have perfectly constructive interference. So how do we know when these two waves emitted by a source will undergo perfectly constructive or perfectly destructive interference? Well, we need to take a look at a couple of examples. We're going to assume for these examples that the source is emitting the waves in phase. In order to ensure that these two waves are going to meet when they are exactly 90 degrees out of phase, resulting in perfectly destructive interference, we need to compare their path length. If we want them to undergo perfectly destructive interference, the difference in their path length has to be an integer multiple of the wavelength, give or take half a wavelength. That will ensure that, for example, when one wave is at a crest, the other wave is going to be at a trough. If we want to ensure perfectly constructive interference, the difference in the path length that they travel has to be equal to an integer multiple of a wavelength. That concludes our summary of wave properties for today.